Okay, we'll just go with that. All right, so hello everybody. My name is Brian. I'm actually a recent alum from the last cohort of Fellowship.ai, where I was based in New York City. Now I'm on externship at Change Healthcare in San Francisco. And today we're going to be speaking about DeepMind's 2017 paper titled Population-Based Training of Neural Networks. So if you have any questions throughout the talk, feel free to just jump in. I might not be able to see your message, so if you just kind of chime in with your voice, that would be helpful. Okay. So first off, just talk about kind of some of the recent successes with neural networks. They've dominated the modern machine learning landscape with success playing Go, Atari, image recognition, and language translation. The success has often been determined by making a series of choices at the start of the research, including on model structure, data presented, and optimization. And so these choices are made via hyperparameters, which are chosen through past experience, random search, or a computationally intensive search process. So the key motivation for this is to really achieve faster speed in terms of wall clock time, cheaper in terms of actual resources consumed, and easier in that less domain knowledge is required and brain power to operate than perhaps other methods. So just an introduction to this algorithm. This is a new method for training neural networks, allowing the experimenter to quickly choose the best set of hyperparameters and model for a specific task. So it trains and optimizes a series of networks concurrently, allowing the optimal setup to be quickly found. Key advantages, it adds no computational overhead compared to previous and popular methods. It's no slower than traditional techniques, and in many cases quicker. Easy to integrate into existing machine learning pipelines, and the hyperparameter schedules and model selection can be automatically discovered. And finally, this results in stable training and better final performance. So this algorithm, it's a hybrid of the two most common methods for hyperparameter optimization, which would be random search and hand tuning. And also is inspired by genetic algorithms. Now let's go ahead and compare and contrast population-based training with these tried and true methods. So parallel optimization, random search being a type of parallel optimization, is where you take a whole bunch of different workers, more or less, and particularly with random search, you just randomize the hyperparameters and initial starting weights, and then you train them all at the same time. Some of them will perform well, most of them will not perform well. And but at the end of the day, you'll just take the one that the weights and the hyperparameters that performs the best. But at the end of the day, with all of the training that leads to bad performance, you're essentially wasting computer resources. And so sequential optimization, which is made up of hand tuning, as well as things like more automated processes like Bayesian optimization. So if we look at hand tuning specifically, researchers take a guess at the best hyperparameters, they train the model using them, and then evaluate its performance. And then they kind of tune accordingly, and this is repeated until the researcher is satisfied with the performance. Bayesian optimization takes this a step further and is able to kind of automate that decision-making process to eventually wean out a strong set of hyperparameters. But it does take a long time, like a long wall clock time, as the model needs to be run many times before finding the best setup. So what population-based training does is by combining random search and hand tuning, you start out with training many neural networks in parallel with random hyperparameters, as in random search. But instead of networks training independently, you use information from the rest of the population to refine the hyperparameters and then direct computation resources towards the models which are essentially performing the best at each given point in time. This is inspired by genetic algorithms in that each population member, we can call it a worker, can exploit information from the remainder of the population. So these are kind of key methods in the PBT code in that when you exploit, you're replacing that worker with a better performer. So say if the performance at a certain given point in time is perhaps in the lowest 20% of all workers, then you would then exploit by looking at the performance of other workers, and you would copy the weights. You would copy either the weights and the hyperparameters or both, and then you would add a bit of noise or some sort of redraw or jigger of the hyperparameters in the explore process. So both key methods in PBT. And then, so after that, you can kind of adapt to the hyperparameter values throughout training, which leads to the automatic learning of best configurations. So any sort of hyperparameter schedule is automatically discovered. So just a recap of these comparison of these methods. So we can see here that population-based training is as fast as parallel search in that you're only actually, in terms of wall clock time, training a single model from start to finish because you're doing a lot of parallel work. It consumes no more resources than parallel search, and the resources are actually directed towards the more promising models. It's easy to implement in that you don't have a bunch of hyperparameter schedules that you have to deal with, as those are discovered automatically. And it reaps the performance benefits of sequential search in that it's able to, in real time, adjust the hyperparameters and weights to arrive at an optimal setup by the end of that single train. So, and then DeepMind in its paper outlines a very kind of rigorous process in order to kind of experiment and better understand the promise of the PBT algorithm. So they look at deep reinforcement learning, machine translation supervised learning, as well as generative adversarial networks. So for instance, in deep reinforcement learning, they run experiments with Unreal on DeepMind Lab, feudal networks on Atari, which is another algorithm, and A3C, yet another algorithm on StarCraft 2. And in the footnotes, I'll send you guys this presentation, and then there's links to all the important papers referring to these algorithms here. In all of these experiments, the population-based training stabilized quickly, found good hyperparameters, and delivered results beyond the state-of-the-art baselines. For the supervised learning, they looked at machine translation on the WMT 2014 English to German with transformer networks, which is essentially a language translation exercise. And both for this and for GANs, this is being compared against a very tried and true, heavily tuned hyperparameter schedule, and they're able to optimize for the relevant metric. Okay. And so this is just another look at the results and performance of population-based training against all of these different domain exercises. So the first three, DM Lab, Atari, and StarCraft, are deep reinforcement learning domain. And so that's compared against the human normalized performance with the same algorithm, but without population-based training. And then the last two, machine translation and GAN, are again the language translation exercise as well as the GAN exercise against the relevant performance metric. Do we have any questions so far?
Yes, I have a question.
Okay.
So what you're running in parallel is basically different trainings with different parameters of the network and so. And what about the case in which you cannot like follow a training further? For example, if you're training with one cycle, you have to start the training over again.
Well, I mean, so the thing is, you can actually do this asynchronously as well, in that when you're setting up this particular run, what you really need is some sort of like common repo or folder, which essentially saves the performance of each worker as well as the weights. And so what happens is every kind of set of certain time steps or whatever, the particular worker will be evaluated against the results of the other workers. And then so all that essentially does is it looks at that folder, looks at the different performances at that particular time step point. And if it's in the bottom certain percentage, then it will choose a more higher performing weight and actually just rewrite itself with that higher performing weight and hyperparameter setup.
Okay.
Yeah, so if you are still working out kind of the specifics in terms of like an algorithm won't train or whatnot, like I think what you're referring to, I think you have to work that out first before you actually are able to run this to completion. Does that make sense?
Yeah, kind of understand.
Okay. Any other questions?
Hey, Brian.
Yeah, just getting a bit of feedback there.
Yeah, sorry about that.
Good Lord. What?
That might happen if someone else has their microphone on as well in the room.
Yeah, we are a couple of people. Okay,
Yeah.
sorry about that.
Yeah,
No problem.
sorry, I don't know why that's happening. Here, we're just gonna. You can do it now.
Is it because of your mic?
No, just guys.
So there can actually only be one microphone in a room. So if more of you have the microphone on, then you'll get that feedback.
Is it echoing now?
No,
that's good now. Yeah.
I muted everything. It's not gonna work.
So can
mute yourself. Aradia, mute yourself.
no, but I'm speaking through my own mic. He has muted.
Yeah, but we can't have two Zooms open in the same room. That's the problem.
Okay.
So you have to exit yours.
Are you guys good?
Yeah, sorry.
No.
Can you hear me good now?
Yeah.
Okay, so the idea that I'm getting here is that there are several optimizations going on across different networks.
Mm-hmm.
And we are basically choosing the best performing set of weights at a given point of time. And we are transferring that to the best performing network, right?
Kind of, yes. That's essentially what it's doing is, so if we just go back to so this diagram is pretty key in that, so basically it's saying that you start out training kind of several workers at once, and then you evaluate them at a certain time step. And we'll also go over the pseudocode in a little bit.
Right.
But so when you have reached that certain time step, then you're comparing it against the performance of the other workers. And if there's a, and these are all kind of like parameters that you set, but if you're in a certain kind of bottom category, then you will just simply rewrite that worker will be rewritten by a higher performing worker at that point in time.
Okay. So as you know that all the optimizations across these deep neural networks are not convex in nature, and maybe the best performing weight for each network is for that specific local minima. How are we ensuring that when transferring that same set of weight to a different network will perform well? Because it might be possible that that other network is has like reached some other local minima and it's been performing well there.
Yeah, and I think that's where you, so as we'll see in kind of later slides, this algorithm performs particularly well when you're using 20 or more workers. So you have a degree of diversification, and that if some specific worker falls into some sort of local minima, then you would probably expect that it wouldn't end up performing well compared to its other workers over time. And so eventually that will just kind of play out, and that will not probably be the final highest performer.
Okay. Yeah, sure. Thanks.
Yep, no problem. Okay, anything else, or I'll just go ahead and continue?
One more question.
Sure.
What's the difference between this and just like normal genetic algorithms where you just take, let's say, some of the best performing ones and make some crossovers to different workers, and it seems very similar.
Yeah, it is similar to kind of normal genetic algorithms. To be honest with you, I don't think that I could properly answer that question in combining discussing the genetic algorithm compared to this specifically. That's kind of like a little bit beyond the scope of this paper. But essentially, I mean, that is what a genetic algorithm does. I would hypothesize without kind of knowing more that it is the combination of the parallel search and the sequential optimization with that genetic algorithm component that is really key to this algorithm. In a genetic algorithm, essentially what you're doing is you're using the setup of previous generations of an agent or whatnot, and in order to tailor the current generation agent. And so that is a component of this model, but there's also the parallelization and the on-time adjustment of the model so that it is actually happening through a single train run. A genetic algorithm, you would typically run a model for multiple generations as well. So does that make sense?
Well, I don't quite understand the distinction, but I would say just go on, and maybe later on when you get to the pseudocode, then I'll see what the differences are.
Okay, yeah, that might be helpful. Okay. Okay, so yeah, so this is, yeah, just move on. So, so another area that they kind of vetted is some ablation studies on the design space of population-based training. So ablation being that they're looking at specific features of the algorithm and to better understand kind of what are the key areas and the key functionality. So here we see, so they take a look at differing population sizes, particularly with training feudal networks on Atari. And so as you could see here, that the performance is not actually great with 10 workers, but when you go up to, for instance, 20 workers, although the performance kind of decreases over time, with at least 20 workers, you're actually performing very well. So, and then in B, they take a look at a couple of different methods for exploiter on GANs. And so for the truncation selection, that is where you rank all the agents in the population by reward. And if the agent is in the bottom 20%, then you sample another agent from the top 20% and you copy the weights and hyperparameters. Binary tournament is where each member of the population randomly selects another member of the population, and if the other member's score is better, then it copies the parameters from the higher score. So as we can see here, truncation works slightly better. And then so in C, we're looking at whether if only the hyperparameters are copied, or if only the weights are copied, or if both are copied. And as we can see, it's actually the combination of the hyperparameters and the weights that are key to this algorithm. And finally with D, so this is essentially the difference between online adaptation of the hyperparameters throughout the train versus actually just running a static set of hyperparameters throughout. So we can see that there is a lot of gain to be made through the adaptation. Adapting being that over time, the hyperparameters actually change. And you can hand program this via some sort of schedule, but that does complicate things. And essentially, this is an automatic discovery of those schedules. Okay, so this is a nice visualization put together by DeepMind, which is it's an evolution of a population during a specific training run. So here they've demonstrated GANs on CFAR 10 and Atari feudal networks. So the initial agents are represented by pink dots, and the blue dots are the final agents. And as you can see down here, as you can see, I think you can see it. Okay. It's color coded. In that the bluer the higher performance in the performance metrics looked at. So the branching of the graph means that the exploit operation has been executed, and so the parameters are copied. And then the paths represent consecutive updates using the step function. Okay. And so now here we are to the pseudocode. So in this algorithm, there's essentially 5 key methods that need to be programmed if you were to implement this. So step, eval, ready, exploit, and explore. So when you're carrying out this algorithm, first you have to declare your population of workers, say 20 workers or so. And then asynchronously, in parallel, and iteratively, you run these different methods where step updates the weights with some form of gradient descent. Then you measure the performance with eval based on the performance metric that you're testing for at a certain given interval that you set. So periodically, a worker will be deemed ready. And so then it will be evaluated. And if it is an underperformer, then you will exploit, as in copying the weights and hyperparameters from a top performer to overwrite that underperformer. And then once you have that new copied worker, then you will actually explore by perturbing the newly copied weights and hyperparameters to sample a higher performing solution space. And then you just repeat until model convergence or the time limit has been exceeded. Okay. So any questions here?
Yeah, Brian. Do they fix the number of epochs or the wall clock time? How do they determine the end of training before they evaluate a worker?
You can actually do both. So it actually kind of just depends on your specific use case. But basically, there just needs to have been enough steps that have occurred that you can actually see a difference through your optimization algorithm, so that you have a basis for comparison.
Okay.
Anything else? Okay, I'll continue. Okay, and then, so I am aware of one implementation of population-based training that it has been implemented by the RAY project, which is by UC Berkeley. The RAY project is a high-performance distributed execution framework targeted at large-scale machine learning and reinforcement learning applications. And so within RAY, the module Tune is a scalable framework for hyperparameter search, which also includes this a PBT implementation. There's actually a toy example available as well, which I've been messing around with, but I think where it's most useful is if you apply it to your specific use case in a hyperparameter optimization exercise. Okay, so just to revisit some of the advantages of population-based training, it takes a single training optimization process. The computational resources are focused on the hyperparameter and weight space with the best chance of producing good results. It allows for an adaptive, automatic hyperparameter selection during training, which has been shown, particularly with learning rates, to improve optimization. And this results in faster learning, lower computational resources, better solutions in many cases, and a simple and easier to use model. And again, that you don't have to mess with complex schedules, etc. Okay. So for more information, DeepMind put out both a white paper, which we're reviewing today, as well as a blog post, which is useful as well. And there's actually a YouTube video discussing the paper as well, which you might want to take a look at. And other than that, that's my presentation. So happy to take any questions that you may have right now. You could also reach out to me at any time. These are my contact details.
Brian, I have a question.
Sure.
I haven't read the entire paper. Do they talk at all about how they perturb the hyperparameters? I realize it's different, like from, like from GANs to something else, but is there like any underlying sort of rules or guidelines that they give?
Yeah, so there's a couple ways to do it. You can simply add noise, or you can pick from some sort of list. For instance, kind of switch up Atom with prop RMS, or just another version of gradient descent, or just some kind of list of ways that you can kind of change the model in a certain respect. So it's discussed in both ways.
Gotcha. Thank you.
I have another question.
Sure.
So Is this method useful in some way for people or organizations that aren't Google, in the sense of, it seems to me that you would still need to have 20 models in like GPU memory. So like that's a pretty high memory requirement. Is there a way around that, or is this literally just designed for the cases where you have a gazillion GPUs and you can run them in parallel?
Yeah, that's a great question. They actually do cover that in the first appendix of the white paper, in that basically you can do this asynchronously as well, in that as I discussed a little bit earlier, you can have just a folder which is shared amongst all the different workers, and then periodically, whenever a worker is deemed ready, then they will both add their information, which includes kind of like the performance, as well as their kind of hyperparameter and weight configuration at that point in time. And then they can evaluate themselves against the rest of the population. So in that way, you could train them all in parallel, as is primarily discussed in the paper. But a place like Google is kind of more cut out for training large models at the same time like that. But again, you can actually just, the process when you're using some sort of shared folder like that and then training asynchronously, it's still much more efficient in terms of resources and whatnot than something like parallel search, where you're just checking a lot of different configurations. Most of them will not work out. Whereas here, you're really focusing on all of the top configurations and then perturbing those top configurations, so that by the end of your process, you will have many different perturbed versions of the top configurations.
Makes sense.
Any other questions?
Sorry, I didn't read the paper either, but I want to ask, which hyperparameters do they search? You mentioned the optimization algorithm. Do they also search things like number of layers, number of nodes and layers?
Yes, yeah. I mean, really, it's a flexible algorithm. They use different hyperparameters for each one of the domain environments that they're testing. So again, it kind of depends on the use case, but what you mentioned are all areas that could be evaluated using this PBT model. And for the specifics, they do list that in the white paper for the specifics of each of the tests that they run.
Nice.
Brian, I got a question.
Sure.
Yeah, so this might be a rookie question. So how do they, so for every worker, do they give the entire data set, or do they bag it and then send it to every worker? What I mean is, does every worker get a distinct set of examples, or everybody gets the same copy?
So in terms of the data set, they're all using the same data set. It's, yeah, when you're talking about kind of initial configuration, it's really just, you could kind of think of a random search, because it starts out as a random search. It's where it starts to differ is after that first time step, where it's saving the different, the performance metrics, as well as the hyperparameters and weights. And then, so it's evaluated periodically, and with a focus over time on the highest performing of all of the different workers. But in terms of the data set, like what has access to what and whatnot, it would be set up exactly as if you would be running a random search on that data set.
Okay, cool. Gotcha. Thanks.
No problem. Okay. Anything else? All right. Well, if any of you guys have any kind of further questions over time, I'll be providing you this presentation, and it'll have my contact information as well. So feel free to reach out whenever you need to. Okay. Thanks, everybody.
Thanks, Brian.
Till next time.
Thanks.
Thanks a lot, Brian.
No worries.